Hello friends, in our last video we had seen how knowledge can be represented, what are the different approaches to represent knowledge, and further we had seen one particular way of logical representation. We had taken help of mathematics, that is propositional algebra, and in the last video we had seen what are the different inference rules which are present in the predicate in the proposition algebra. There are over 18 rules that we saw last time. Now, my suggestion to the students is before you begin seeing this particular video, make sure that you are well versed with those formulas that we have discussed so that at any point of time you'll be able to use these formulas without hesitation. Now, we will proceed with part 2 of the propositional algebra, wherein we are going to now see how English sentences can be represented using the propositional algebra so that the initial fact which is in English can be easily converted to propositional representation of the facts. So we will take a quick example. Suppose there is a sentence, okay? Uh, I will get wet if it rains and I go out of the house. Let's say this is a sentence. I will go wet if it rains and I go out of the house. Now, first of all, uh, one thing is very clear that this is not an atomic proposition. Why? Because there are many sub sentences which are present in this sentence. Okay. If you look at this particular view, okay, see that I will get wet is one sub sentence. The first sub sentence is I will get wet. Second sub sentence is it rains, right? I will get wet is first sub sentence. It rains is the second sub sentence, and the third sub sentence present in this particular sentence is I go out of the house. And all these three sub sentences are connected with certain connectives. For example, here and that connects it rains and I go out of the house, and also connective if that connects I will get wet and it rains. So then in such kind of molecular or complex propositions, how can we represent a sentence, a proposition sentence? So let's begin. Let the propositions be, let W be the proposition that I will get wet. So this I will get wet sub sentence, I'm using proposition W to represent that sentence, right? So that means if not operator is coming before W, then it will mean I will not get wet. Okay. So let W be the proposition that I will get wet. Okay. Now I will use another proposition R to represent it rains. So let R be the proposition that it rains. And let S be the proposition that I go out of the house, right? So each sub sentence I have represented using three different propositions W, R and S. And now to represent this full sentence, okay, with its ornaments, that is if, and so on, I will have to make use of uh, the the rules that we have seen in the previous lecture, right? So carefully observing this sentence, you will realize that the implication of this is that I will get wet. Okay, it means suppose it rains, and while it is raining, suppose I go out of the house, then I will get wet. The sentence means what? If it rains and I go out of the house, then I will get wet. So R and S implies W, right? So this is how a proposition can be represented. So this entire sentence, English sentence, higher level representation, can be converted to equivalent internal representation using propositional algebra, that is this. So let us read it again. Now S means I go out of the house. So if I go out of the house, and means connective conjunction, and it rains. Or that means if I go out of the house and it rains, if both these things are true, implies I will get wet. W. Right? So this is how we can make use of the connectives like and or conjunction or disjunction, not or negation, right? Implications, by implications. So we can make use of these to represent the molecular propositions. Let's continue. Okay, let's continue. We'll see some examples how simple facts can be represented using this method. It is raining. Okay, it can be represented with just one word, raining. So let raining be the proposition that it is raining. So if not comes in front of raining variable, then it means it is not raining. It is sunny can be represented with just one word, sunny. Or you can even say let S be the proposition that it is sunny. It is windy can be represented with windy. And now all these three sub sentences are used in this bigger sentence. Okay, in fact only two, raining and sunny. Windy is not used. So if it is raining, then it is not sunny. That means raining implies not sunny, right? Sunny is a variable that represents it is sunny. So when you apply not sign before sunny variable, it means it is not sunny. Okay, so this is how propositions can be represented. Now this propositional logic sentences, they have to be normalized. So there are two normalization forms which are available. The first one is called as conjunctive normal form. Okay, so this is an example of conjunctive normal form, wherein it is basically, what is conjunctive normal form? There are disjunctions. So whenever any proposition is connected with or, like P or Q or R, that's a disjunction. So looking at this particular sentence, the various disjunctions are, the first disjunction is P or Q or R. Agreed? Because each proposition is connected with or only. If a proposition is connected with and, or is it a mix, if it is a mixture of and or, that's not a disjunction. Disjunction is the term in which each proposition should be strictly connected to other proposition using only disjunction or, right? The second proposition, the second disjunction in this sentence is P or Q, third P or R, and fourth is P. Now you'll wonder why this P is also a disjunction. You remember your idempotent rule? Idempotent rule states, if P is a proposition, then P disjunction P, that means P or P gives P itself. So using that definition, P can be also written as P or P. So single proposition P is also a disjunction. Similarly, if required, you can also consider single proposition P as conjunction wherever it is required. Why? Because P can be also written as P and P. Okay, again it is idempotent rule. So conjunctive normal form is nothing but it is conjunction of disjunctions. Conjunction means when different disjunctions 1, 2, 3, 4, when different disjunctions are connected with a conjunction, then that's called as conjunctive normal form. These are conjunctions. So different disjunctions, when they are connected with conjunction, that's called as conjunctive normal form. And in AI, disjunctions are also called as clauses. Very important. Okay, so what are clauses? When one or more propositions, they are connected with or disjunction, that entire term is called as a clause. Okay, so in AI, this conjunctive normal form, we are going to also call it as a clausal form. Please remember the term. We are also going to call it as, refer it as clausal form. where different clauses are connected using AND. Okay, and also remember that in AI, later on I'll show you, there is an algorithm called as resolution, which is used for inferencing, right? So resolution algorithm, whenever you're going giving input to this resolution algorithm, the sentences, predicate, the proposition sentences should be always in the clausal form. Only then the sentences can be given as input, otherwise not. Now in propositions there is also another normal form that is called as disjunctive normal form. Now this disjunctive normal form is something which we will not use in AI. We will mostly deal with conjunctive normal form, but it is what? It is basically, it is disjunction of conjunctions. Now you see, P and Q and R, when propositions are connected with only and, then that's a conjunction. So when different conjunctions are connected with or, then it becomes disjunctive normal form. We are not going to discuss any further disjunctive normal form because we are not going to use it, right? Now next, as I've told you, uh, the resolution algorithm, which is an algorithm or internal program that will take as input the internal sentences in internal representation in the logical form, and it will deduce something new, or it will infer something new out of those sentences, right? So the resolution algorithm always takes as input proposition sentences which are in the clausal form or in CNF. So that's why for exam also, whenever an English sentence is given to you, okay, you have to first convert it to the clausal form, you have to first convert it into a proposition form. Whenever English sentence is given to you, you have to convert it into proposition form, and then make sure that that proposition form is also in a clausal. If the proposition that you have represented is not in a clausal form, then it is your duty to convert that proposition into clausal form or into CNF. So next we are going to see the procedure to convert a given statement to CNF. Okay. Now the first step of the procedure is, if at all there are implications or biconditionals, that means by implications, in your proposition sentence, if at all there are implications or biconditionals in your proposition sentence, then you need to eliminate those first. Now to eliminate implications and biconditionals, we already have the formulas with us. Okay, this is the by implication elimination formula. So P implies by Q can be written as P implied Q and Q implies P, and this can be further written as not P or Q and not Q or P, right? So you can make use of this formula wherever there is by implication. You need to eliminate it. Similarly, single implications can be eliminated using this formula, which we had already discussed in the last video. P implies Q can be written as not P or Q. So whenever you get this proposition sentence, and if the sentence is not in CNF, the very first step that you're going to do to convert it into CNF is, if at all there are implications or biconditionals present in the sentence, use these formulas and try to eliminate those things. Now the second step here is application of De Morgan's law, and reduce not symbols so as to bring negations before the atoms. Okay, what it means is, if there are negation symbols appearing before a sub expression, then that negation has to be substituted inside the sub expression for each and every term of that sub expression. So this is De Morgan's law. Example, you see here, negation is present outside a sub expression P or Q. So when this is there, your aim is now, De Morgan's law, what it does, it applies this negation to each individual term inside the sub expression. So when not is applied to P, it becomes not P. When not is applied to disjunction, it becomes conjunction, and when not is applied to Q, it becomes not Q. So this is one formula. Now same thing is applicable when here instead of disjunction it is conjunction, right? So when not is applied to P, it becomes not P. not is applied to conjunction, it becomes disjunction, and not is applied to Q, it becomes not Q, right? One more thing which I have not discussed here before I go to the third step, double negations. Okay, not of not P is equal to P, right? Double negations are supposed to be addressed in step 2, which I am not shown. Step 3. Now, once implications by conditionals are eliminated, once De Morgan's law is applied, not is substituted for each of the term. Now, you can use distributive law or any other law, equivalent formulas. We have seen 18 formulas in the last video. So, you can use those formulas to obtain the expression into CNN, right? So briefly we'll see one example how to convert a given predicate given proposition sentence into CNN. Suppose this is a sentence given to you: P implies Q implies R. Okay, now is this in CNF? No. So there is a need to convert this into CNF. So as the first step, you are going to uh, eliminate implications, because there are two implications here: P implies Q and this whole sub expression implies R. So first you're going to solve the innermost bracket. Okay, solving the innermost bracket, this term can be then written as not P or Q, right? So P implies Q implies R. The first step, you're going to eliminate the implication. First, the innermost implication you're going to eliminate. So this term will be written as not P or Q. Fine. Implies R. So the innermost implication is eliminated. Then we are going to eliminate the outer implication. So this whole term can be then written as not of this whole term or R. Correct? Not of this whole term or R. Now, the implications are all eliminated. Correct? But is there any negation sign standing outside any sub-expression? Step number 2, that is De Morgan's law. Yes, there is a negation sign here standing outside a sub-expression. So using De Morgan's law, now we have to substitute this negation inside for each of the term. Okay, now see, double negation works here. Not of not P will become P. Not of or will become and not of Q will become not Q. So the sub expression will be, okay, the sub expression will be not of not P will give you P, not of or will give you and not of Q will become not Q. And this R can be written as it is, or R. So this is the term that we are going to get after step number 2. Now what is step number 3? In step number 3, we have to use either distributive rule or any other rule, so that the entire expression over here gets converted into CNN. Now looking at this, okay, looking at this sub expression that we have in front of us, conjunctive normal form is nothing but it is a conjunction of clauses. Okay, when clauses are connected with and. Now what is a clause? So if I use the distributive rule here, then this can be written as, okay, R or P and R or not Q. Correct? So R or P and R or not Q. Right? I've just used distributive law here and I get this term. Now is it in CNF? Yes, it is in CNF. Right? So likewise, any sentence, English sentence that is given to us, our duty is to first convert it into proposition sentence. But every proposition sentence may not be in CNF or may not be in clausal form. So now we will have to use this procedure, the 3 steps which I mentioned before, like this, to convert that non-CNF form to CNF, non-clausal form to clausal form. And then only this kind of sentence can be given as input to the resolution algorithm. Having discussed the prerequisites, okay, now let us move to the resolution algorithm itself. So next we are going to see the resolution algorithm in proposition logic. It is basically proof by refutation or proof by contradiction algorithm. Okay, it is used for theorem proving or rule of inference. Okay, now let's see the method here. Assume that we have to prove proposition A. Okay, assume that we have to prove a proposition A. Now since it is proof by refutation, we start by assuming that let A be false. We have to prove A is true. So we start by saying that, assume that let A be false, and that means not A is true. We are asked to prove that A is true. So let us assume that A is not true. So not A. Correct? Now this term not A, you add it to the set of statements in your uh, knowledge base. Okay, and now continue solving the algorithm starting from not A. Continue solving the algorithm starting with not A, and if you get a contradiction false at the end, it means your initial assumption that is not A is false, and hence the original proposition which is asked to be proved, that is A, must be true. Okay, now every time, again I am telling you, every time when I use a word called as clause, what is clause? It is disjunction of literals. Okay, clause is nothing but disjunction of literal. So I am going to use this word clause again and again, but it is basically disjunction of literals. And when different clauses are connected with n, that's a clausal form or CNF. Okay, now it is always good that any algorithm that we see, we also solve it and we see how it works. So let us see how this resolution algorithm works for propositional logic. Okay, let us take an example. Suppose the machine is given, suppose machine is fed with this particular sentence. If it is hot, then it is humid. First sentence given to the machine is, if it is hot, then it is humid. Second sentence, if it is humid, then it will rain. Third sentence, it is hot. What is asked to prove? Prove that it will rain. Now when this thing comes, okay, so three sentences are given. These are the known facts to the machine. The first sentence known to the machine is, if it is hot, then it is humid. Correct. Second sentence which is given as input to the machine, so this is also a known fact to the machine, that if it is humid, then it will rain. And third fact which is given to the machine, known to the machine, is that currently it is hot. And the machine is asked the query, will it rain, or prove that it will rain. So what machine will do? It will use this resolution algorithm and prove whether it will rain or whether it will not rain. So before using the resolution algorithm, as I told you, these English sentences cannot be directly represented in the knowledge base of the agent. So they have to be converted to the internal representation, in my case here in the proposition sentence. So let's first convert these sentences into the propositions. So I will be using three propositions. Okay, so let us denote these statements using propositions H, O and R. Okay, so let H be the proposition that it is humid. It is humid is represented with H. Let O be the proposition that it is hot. Let H be the proposition that it is humid. Let O be the proposition that it is hot. Okay, so here also it is humid, humid is there, and there is another proposition which is required, it will rain. So let R be the proposition that it will rain. So all the sub sentences are represented with the propositions H, O and R. So the first sub sentence, it is hot, is represented with proposition O. Second sub sentence, it is humid, is represented with H, and third sub sentence, it will rain, is represented with R. So now the first thing is, we have to convert each of this English sentence into the proposition sentence. Okay, so the first sentence if it is hot then it is humid can be written as O implies H, because O means hot, so hot implies humid. If it is hot then it is humid, that means hot implies humid. Now once you convert a sentence into proposition, ultimately you're going to use resolution algorithm for this. So it is your duty to see whether this is already in CNF. Is it in CNF? No, because there is implication sign here. So again we'll be using the procedure that we saw earlier, and the first step of the procedure tells me that I have to eliminate the implication. So O implies H can be written as not O or H. Now is the sentence in CNF or clausal form? Yes, because this is an individual clause, so it is in CNF. Okay students, remember whenever I say clausal form, it may be just single clause or it may be set of clauses connected with end. Both these cases are always clausal form cases. So you see this thing is a single clause, there is no end here, but still a single clause is also in a clausal form or CNF, right? So it is in CNF now or clausal form. Let's head on to the second sentence. Second sentence is, if it is humid then it will rain. Okay, H is a proposition for humid and R is a proposition for rain, so this can be written as H implies R. That means if it is humid implies it will rain. Now again this is not in your CNF, or this is not a clausal form, so implication can be eliminated by writing not H or R. Now is this a clausal form? Yes, right? So this sentence is added to the knowledge base. In my previous case, this sentence will be added to the knowledge base and not this. So the clausal form sentences or the clauses will be added to the knowledge base. Always remember. Okay. Now third, it is hot. Now it's very simple. It is hot and O is represented for hot. Okay. Now single O, it is already in clausal form. I told you a single term, a single proposition using the property that is idempotent rule. P implies P or P. So here O implies O or O. That means single proposition is also in a clause. So this is already in a clausal form. Now what is asked to prove? It will rain. Okay, so we have to prove R is true because R is a proposition representing it will rain. Okay, so I told you these are the sentences which we have. How do we start with resolution? The first, it's a proof by refutation algorithm. So the very first thing is we have to assume that it will not rain. They have asked you to prove that it will rain, so we will start by assuming that it will not. So let us assume that it will not rain. That means not R. And now this not R is also added to the knowledge base along with the other sentences. So let us recapitulate what is there in the knowledge base right now. Not R is present in the knowledge base. O is present in the knowledge base. Not H or R is present in the knowledge base. And not O or H is present in the knowledge base. So these are the things present in the knowledge base. And now we have to use the resolution algorithm. Okay. Now in this resolution algorithm, we are going to use the formulas. In fact, we are going to use two formulas. The first formula is, if any proposition is ended with false, it ultimately gives you false. Any proposition when ended with false, it ultimately gives you false. Right? So what is a resolution algorithm? Let's start with not R and we'll take another sentence not H or R. Okay, our aim is what? We will try to cancel out not R with R, and this way our aim is to go on cancelling out the terms so that finally no term remains and we are going to get contradiction, or it is also called as empty clause. Okay, so we take it will not rain as one sentence and we'll take this sentence and we are trying to resolve them together. Now notice that this in the resolution algorithm, this means AND. Okay, in the resolution algorithm, this means AND. Fine. So not R and R gives you what? It gives you contradiction, that is false. So that means not R and R will cancel out, so it is false, right? So any term and false always gives you false. So one term here is not R, and in this term is in this sub sentence there is R, right? So not R and R is a contradiction, so this will get cancelled out. So that means, so not P and P is always false, so the ultimate answer here is false. Okay, ultimate answer here is false. Now any term or false always gives you that term, so not H or false. So what is the resolvent? It is going to give you not H. Okay, try to understand this, how resolution works. See, basically our assumption is that it will not rain, so not R is considered, correct? So resolution algorithm, the very first thing, you should start with that term, your assumption, and there will be other sentences in the knowledge base, 3 sentences basically. So you have to choose such sentence. Okay, you have to choose that sentence which has an element that can be cancelled out with this not R. Okay, so if you consider the previous sentences, here there is R that can be cancelled out with not R, no, so sentence 3 cannot be used. Here there is an R that can be cancelled out with not R, yes there is R, so sentence 2 can be taken. Similarly, can I take sentence 1? No, there is no R here, so I cannot take this sentence. Understood? And that is why, to cancel out this not R and R, I am resolving this term and this sentence like this. That's why I'm taking not R. Not R, I have to begin with not R only. But then why I'm taking this particular sentence? Because there is R that can be cancelled with not R. Okay, and these arrows, it means AND. So not R and R gives you false, so you will get false here, or they get cancelled out. And not H, that means any valid term or false always gives you valid term. So this is the logic behind resolution algorithm. So in my later examples, even in the predicate logic that I'm going to teach you later on, whenever resolution comes, the same methodology I'm going to use. Right? Now, once you get this term, remember, once a particular sentence is taken, that sentence cannot be resolved again. You cannot take it again. So now, not R is taken, not H or R, both these sentences are taken. What remains? Okay, this sentence is taken, this sentence is taken. What remains? Sentence number 3 can be taken, can be taken, or we can take sentence number 1, not O or H. But current resolvent that we have got is not H. So it will be better if I take sentence number 1 which has H, which can be cancelled with not H. Okay, so I have not H, so I am taking a sentence not O or H, that is sentence number 1. Why? Because I can cancel out this H with not H. So again, not H, so when these two sentences are resolved, not H and H will cancel out, and the resolvent that we are going to get here is not O. Correct? So since sentence number 1 is taken already, sentence number 3 is taken already, you cannot take them again. So what remains? Sorry, sentence number 1 and sentence number 2 are already taken, you cannot take them again. Even this sentence is taken. So what remains? Sentence number 3 remains. And what is the resolvent that we have currently? Not O. So after taking sentence number 3, that is O, and not O can be cancelled out together. So that means not O and O is what? False. And false is also represented with F or E. So E means empty clause or contradiction. Fine. So what we have done, starting with our assumption that it will not rain, we started resolving each term or each sentence, and finally we have reached an empty clause. Okay, empty clause is a clause wherein we get contradiction or false, F. So then finally we say, since an empty clause E has been deduced, we say that our assumption is wrong. Our assumption that it will not rain is wrong, and hence what we are asked to prove, okay, that it will rain is true. So this is how this is a method, this is how uh, the machine, AI machine, is able to convert, is able to deduce new conclusions, is going to infer new things from the known facts in the knowledge base using this proposition logic. Fine. Now, using propositional logic, the theorem proving is decidable. That means yes, you can get the answer. But the problem here is what? This propositional logic, it cannot represent objects and quantifications. Okay. Now, I'll talk about this. Okay. What is quantification? Now, all the sentences which we have seen so far, they were one-to-one sentences. There are no quantities involved. But if I say all dogs have tail, now when I say all dogs, it is not one dog I'm talking about. It is all the possible dogs, all the dogs, right? So this is quantification, quantity. So such quantities cannot be represented using your simple propositional algebra, right? Similarly, objects cannot be represented. So for example, if there is a sentence, okay, John is a man. So if I ask you to convert this into proposition logic, how will you write? Let M be the proposition that John is a man, right? So when you represent the whole sentence with a one word, say M, will you be able to distinguish which is an object? So you know that, or if the question is asked to the system, okay, who is man? Will the system be able to answer that John? No. Because what happens is propositional logic, the entire sentence, without knowing the exact meaning of the sentence, the entire sentence is treated as one term, right? Or maybe conjunction or of different terms. So you call it as a molecular proposition, okay? But it cannot deduce the meaning of the sentence, and that's why propositional logic, even though it is powerful, even though it gives the answer, but it cannot represent objects. It cannot represent objects and the relations among two or three objects in the sentence. And the quantities also cannot be represented in the propositional logic. So although a very powerful mathematical concept, it fails, and we have to refine this further, and we go for the next kind of concept that is called as predicate logic. So predicate logic is basically based on this propositional logic. We have not totally discarded propositional logic. It is based on the propositional logic, but it is at higher end. Okay, so that's all for this particular lecture. In my next video, we are going to then see what is predicate logic and then how it can be used for inferences. Thank you.